Okay, so this is section 3.2, day 1, and we're talking about extrema. Extrema is the plural, extremum is the singular. So up at the top, the definition of a relative extremum is a point where the function changes from increasing to decreasing. And if that's what's happening, it's called a relative maximum, or decreasing to increasing, and then you have a relative minimum. So if you remember from before spring break, section 3.1, we were talking about how to figure out where our function changes from increasing to decreasing and decreasing to increasing. And now we are going to label that point where it does as an extremum. So the definition of a relative extrema there is let f be a function defined at c. So c would be an x value. The function value at c is a relative maximum if f of f, if there exists an interval ab such that the function value at x is less than or equal to the function value at c for all x in that interval. So what that looks like is if you have a function and at the value c, then you have an interval around it. So maybe a is over here and b is over here. So a and b are surrounding c. But the function value at any point other than c is less than the function value at c. So in other words, the function value at c could be up here. But any other place in this interval, the function value is less than that. So any other value in there, it'd be less than that. And that would make your, do something more like this. That would make your value C the extrema because the function value is the greatest in that interval. And that's what makes something a maximum. The function value is the greatest in the interval, a relative maximum. A relative minimum, same idea. If you have that same value of c and you have an a and a b surrounding it, so a little interval around that value of c, and for all the x in that interval, that's what this little symbol means, element of. So for all the values of x in that interval, the function value of those x values is greater than the function value at c. That makes this value of c the function value at c a relative minimum. So it is the lowest function value of all the function values in this interval. So all the other ones are greater, and that would make it a relative minimum. And so these are the things that we're going to be looking for, these x values that give us a relative minimum or a relative maximum. If f has a relative extremum, one of these minimums or maximums at c, then c has to be a critical number. And those are what we were finding in section 3.1, the critical numbers. And critical numbers occur when the derivative of the function is 0 or the derivative of the function is undefined. So these critical values are going to be the things that we're looking for again. And then we're going to test to see if those critical values turn out to give us a maximum or a minimum on the interval. And so that's what this first derivative test is right here. It says that if we have our function is continuous on an interval, and we talked about what continuous means. It means we wouldn't pick up our pencil when we were drawing that function from A to B. And if C is the only critical number in that interval, if f is differentiable on the interval, and that means that it doesn't make a real sharp turn, and it's continuous, we already said that, then f of c can be classified as a relative minimum, maximum, or neither. So if you find a critical value, you then have to determine, is it a maximum, is it a minimum, or is it neither? And it can be any of those three things. So here is where we can see what that looks like. So on the interval, if the derivative is negative to the left of c and positive to the right of c, then we'll have a minimum, and it'll look like this. This would be the x value of c, and the derivative being negative to the left looks like that, and that means your function's decreasing. And then if all of a sudden then to the right of your c, the derivative is positive, then you must have found a minimum. On number 2, if it's the other way around, this is your x value of c, and to the left of c, the derivative is positive, meaning it's increasing, and to the right of c, the derivative is negative, then you found a maximum. The third possibility, though, is on the interval, maybe your derivative is positive on both sides of c, or negative on both sides of c. And then if that's the case, you didn't find a relative extrema. And that would look something like this. Here is an example. If this is your value of c, and you look to the left of c, and your function is decreasing because the derivative is negative, but it's still decreasing to the right of c, then this thing is not an extremum. It is a specific kind of point. It's called an inflection point that we're going to learn about later, but it's not a maximum and it's not a minimum. It still is a critical value. C is still a critical value because the derivative at this point is undefined. The slope of the tangent line right there is undefined. And so C would come up as a critical value, but when you checked it to see if it was a max or a min, you'd have to say, oh, it's neither. And the same thing would be true here. If this is your critical value of C, something critical is happening to the curve right now, but it's not a maximum or a minimum. Because when you look to the left of C, your derivative is positive because your curve is increasing. And to the right, it's also positive because it's still increasing. But at that particular point, the slope of the tangent is undefined. And so it's a critical value, but not a maximum or a minimum. So in other words, when you're trying to find these maximum and minimum, these extrema, you're going to find the critical values, and then you're going to test them to see if they are maximum or minimum. So a couple examples of what that looks like are on the second page. And here's an example of a polynomial. So we probably have an idea of what this function looks like already, but we're going to look and see if we can find any extrema on this function. So the way we're going to go about it is the first step is we're going to take the derivative, and the derivative of this is going to be 6x squared minus 6x minus 36. And then we're going to try to find critical values by, in this case, simply setting the derivative equal to 0. Because the other possibility is we might have to see if the derivative is ever undefined, but a polynomial is never undefined. So we're just going to set it equal to 0, factor out a 6, factor out x squared minus x minus 6, and get two critical values of 3 and negative 2. So they're my critical values. Those are the places where the derivative is 0. And after you do that, we're going to do what we did in section 3.1, so this is going to look really familiar. We're going to set up intervals from negative infinity to negative 2, negative 2 to 3, and 3 to infinity. and we're going to check the sign of the derivative. So negative number like, say, -5, if you plugged it into your derivative, would be 6 times -8 times -3. That would be a positive value. A number like 0 that lives in here would be 6 times -3 times 2. That would be a negative value. And a number in here like 5 would be 6 times 2 times 7. We'd be positive again. So in section 3.1 we would say, okay, our function is increasing and now it's decreasing and now it's increasing again. And the new part for section 3.2 is, oh, I just found a place where the function went from increasing to decreasing. So it looked something like this. I just found a relative max. And when it went from decreasing back to increasing, I found a relative min. So what we're going to say now in this section is the relative max is occurring when x is -2. And then I've got to plug the -2 back into the function to find the y value. So we're going to have to get a y value for my relative max. And the same thing for my relative min. That's occurring when x is 3. But again, I've got to plug it into the function to get the y value. So again, I didn't bring a calculator with me, unfortunately, so I'll have to do this by hand. -2, when I plug it into there, I'm going to get -16 minus 12 plus 72 plus 14. So -28 plus 96. So it looks like it's 68. Hopefully I did that right. And when I plug 3 in, I'm going to get, hold on one second. Sorry, I had let my dog out. Okay, so 3 is, I'm going to plug 3 in and I'm going to get 54 minus 27 minus 108 plus 14. So that's 68 minus 135. So that's -67, I guess. So hopefully I calculated those right, but if you have a calculator, you can double check me. All right, so again, it's just one more step from section 3.1. All we're doing is labeling these places where the function goes from increasing to decreasing or decreasing to increasing. Looking at number 2, same idea. First step is to take the derivative. So 12x squared minus 6x. Second step is to see where that derivative is equal to 0 or undefined. But in this case, it will not be undefined anywhere. In order to find this, I'm going to factor 6x out and be left with 2x minus 1. And then I'm going to get my critical numbers, or my critical values, of x equals 0, which makes this piece 0, 6x. And x equals 1/2, which makes the other one 0. I'll be right back again. So I have 2 critical values, and I need to set up my intervals from -infinity to the first one, which is 0, from 0 to the second one, which is 1/2, and from 1/2 to out to infinity. And see what happens to my function around these 2 critical values. So the derivative is what I'm going to check, the sign of the derivative. A negative number like -1 would make this piece 6x negative, and it would make this piece negative, and when you multiply them together, it would give you a positive value. Now I got to pick a number in here. This is a pretty small interval, so I don't have a lot of choice. I'll pick like a fourth. And a fourth would make this positive, and a fourth would make this piece negative because it would be a half minus 1. So I'd have a positive number times a negative number, so that'd be negative. And then I'll pick a number like 10 that lives in that interval. 60, 19, both positive. You multiply them together, it's positive. So again, this line that you're doing right here, you could do it on your calculator if you want. I'm not picky about what the value is. I just want to know what the sign is. So however you want to come up with that, once you get those signs, then you can figure it out very quickly. Your function was increasing, and then it decreased, and then it increased again. So obviously we found a maximum here because it went from increasing to decreasing, and we found a minimum here when it went from decreasing to increasing. So our relative maximum is 0, comma, and then we got to get the y value. So I'm going to plug 0 back into my function, my original function, and it turns out to be 0 for my y value. And my relative minimum is 1/2, comma, I'm going to go back to my function and figure out the function value of a half. And that'll be 4 times an eighth, which is a half, minus 3/4. So it should be negative 1/4 as my y value. If you plug these values back into your derivative, you're going to get 0. That's what they are. They're critical values. They make your derivative 0. So always get these y values from plugging them back into your function. Last problem. This is not a polynomial, so we're going to have to think about it a little bit. When we take the derivative, we are going to use the simple power rule, so it's going to be 2 minus 2x to the negative 1/3. Pull the 2/3 down, and when it multiplies by 3, that's 2. Drop the degree to negative 1/3. So we've got to figure out when this is equal to 0 and when it's undefined, because a negative exponent means that it will be undefined at some point. So the way we're going to do that is we're going to factor out the lowest degree. So it's no different than the previous problems. We're factoring to figure this out. But in this case, we're going to pull out x to the negative 1/3, and we can also pull out a 2. They both have a 2. So when we do that, what we're going to be left with is, from this term, we have to think about it carefully. There wasn't an x, so how did I pull out an x to the negative 1/3? Well, there really was an x. It just was to the 0 power. So if you imagine that, then you can subtract your exponents. The old exponent minus what you pulled out is going to be x to the positive 1/3. So anytime you want to pull out an x to a negative power and you have a constant, you can do it still. You just have to be creative about it. And if you check it, when you distribute back, the negative 1/3 and the positive 1/3 will make it x to the 0, which makes it have no x term. X to the 0 is 1. So that's a check. If you multiply these two, you're going to get back to the 2 that you started with. And then over here, you pulled everything out so that you would have a 1 left. And we can then set it equal to 0 to see where it's undefined and where it is equal to 0. So what we've done in the past is we've kept everything with a positive exponent in the numerator and taken what had a negative exponent to the denominator and created this fraction. And the reason I had you do that was for this very moment, because if you want to find the critical values, you need to set the numerator equal to 0 and the denominator equal to 0. So you're going to have a critical value at x equals 0 because that's where the derivative is undefined. So you're finding that your derivative is undefined when x is 0. That's a critical value. You're also going to find one when x to the 1/3 minus 1 is 0. Or when x to the 1/3 is 1. Or if you cube both sides when x is 1. And that's when your derivative is 0. So that's a critical value. So we have a critical value of 0 and of 1 in this problem. And so we're going to go to our intervals, which come from the number line, go from -infinity to 0, go from 0 to 1, go from 1 to infinity. And check the sign of our derivative. So if you plug a number like, I'm going to pick perfect cubes because this is a cube root, -8. -8, the cube root of -8 is -2 minus 1. That's going to be a negative value. This is positive, so my numerator is all negative, but so is my denominator. That means my function's derivative is positive there. If I pick a number like 1/8, this would be the cube root of 1/8, which is a half. When I take 1 away, this will be negative, but the denominator will be positive. So my derivative will be negative. And a number like 8 will give me 2 times 1 over 2. That's positive again. This is where you have to be very careful, because if you think about this problem and you think my function went increasing, decreasing, increasing, you have to make sure that these places where the graph is turning exist on your function. So is 0 in the domain of your original function? It is. You can plug 0 into your original function. Is 1 in the domain of your original function? Yes, it is. So because these two critical values are in the domain of your function, they can be extrema. If they were not in the domain, then they would not be extrema. They might be an asymptote, or they might be a hole. But the critical value came from the fact that the derivative was undefined. But you want to make sure that the function is defined there, and it is. So we can go ahead then and say that I found a maximum here and a minimum here. So my relative max is 0, comma, plug 0 back into your original function and you get 0 out. And my relative min occurs at 1. Plug 1 into your original function and get -1 out. So there's my relative min. And you can check yourself if you have a graphing calculator by graphing it and seeing if it looks like what you just said it does. Is the max where you said it was? Is the min where you said it was? And I'm fine with you checking the problem that way, but without all the work that I've shown, you won't get credit on a test, because I know you can plug it in your calculator and see these things. I need to see the work involved and how you got your critical values and how you checked your critical values. So that's section 3.2, day 1. We'll pick up Tuesday with the second half of this section.